everyone. Thanks for coming for the first summer CITA seminar of 2024. We have a speaker, Kremer. He's moving to UC San Diego for an assistant professor soon, late September, right? And he was a Hubble Fellow at Caltech, and he's an expert on globular clusters, gravitational waves, and transients. So Kyle, please take it away.
All right, sounds good. Thanks, Claire, for the intro. Happy to be here. So, yeah, in the past 10 years or so, there's been a lot of sort of updates to this topic of compact objects and clusters. So, a lot of simulation advances, a lot of observational advances that have really sort of reshaped our understanding of the various dynamical activities of compact objects and clusters. So, my sort of goal of this talk is to give sort of an overview of the current state of the field from the observation simulation perspective, and then sort of discuss some of what I think are sort of the more exciting applications of this topic to a few of the sort of current topics in astronomy, both now and looking forward over the next few years to decade. So I wanted to start with just a picture from HST of a very typical Milky Way globular cluster. So this is M22. It's one of the closer globular clusters to Earth, so it's been very well studied by HST, also by many other telescopes over the years and decades. So like most of the Milky Way clusters, M22 has around 100,000 stars, although many clusters in the Milky Way can be larger than this, up to 1 million or even a little bit over 1 million in some cases. And this cluster is also very compact, so the typical half-light radius of clusters like M22 are of order a parsec or a few parsec. So, of course, the combination of the large number of stars and the very compact radius means these systems are really dense. So the central density in a typical cluster is thousands to tens of thousands of stars per cubic parsec. And just for reference, the stellar density of the solar neighborhood is less than 1 per cubic parsec. So these are thousands of times denser than sort of typical galactic field environments. So certainly these high densities set the stage for large numbers of strong gravitational encounters between objects that would never happen for stars living in a typical galaxy. And aside from their densities, the other sort of defining feature of globular clusters is their very old stellar population. So 10, 12 billion years old. The Milky Way's globular clusters contain some of the oldest stars in the galaxy. So this makes globular clusters really nice tracers of the formation and assembly history of the Milky Way. So this is a sort of edge-on simulated image of the Milky Way and its globular cluster population. So most of the globular clusters are distributed roughly spherically in the halo of the galaxy. There's also a subset, a fairly large subset of clusters that are found in the disk. So here's M22, it's one of the disk globular clusters. So there's about 160 known globular clusters in the Milky Way. There's almost certainly another 40 or 50 or so behind the bulge of the galaxy that are hidden from our view just because of the bulge. So there's probably something like 200 globular clusters in the Milky Way. And the Milky Way globular clusters in particular have been very well studied for decades, even over 100 years in some cases. But more recently, thanks in large part due to HST, it's now very well understood that globular clusters are common features of essentially all types of galaxies. So recently, we've begun to discover globular clusters in lowest mass galaxies, these ultra-diffuse dwarf galaxies. So these dwarf galaxies typically contain of order a few to maybe tens of globular clusters in their halo. Again, spiral galaxies like the Milky Way and Andromeda generally contain of order a few hundred globular clusters. And then the most massive elliptical galaxies can have thousands, even tens of thousands of globular clusters. So the best example in the local universe is M87, which has of order 10,000 globular clusters, mostly in its halo. So these are really common types of systems throughout all galaxies, throughout the local universe. So again, M22 is a very typical galactic globular cluster, and as best as we can tell from extragalactic cluster observations, this is also a very typical extragalactic globular cluster. So the one sort of special feature about M22 that makes it unique especially amongst the Milky Way, is that in its center, it's host to two observed stellar mass black holes. So these were both found about 12 years ago now. These are both accreting black hole binaries, or accreting material from a binary stellar companion, and they're observed as X-ray and radio sources. So when these two sources were found a little over 10 years ago, this was actually the first clear observational evidence for stellar mass black holes in present-day globular clusters. And a lot of work since has shown that, in fact, the presence of black holes in globular clusters is actually very common to most globular clusters. And the current sort of state-of-the-art, or sort of current state of the field, suggests that most clusters contain tens to even hundreds of black holes in their centers today. So this is sort of one of the big points that I'm going to make throughout this talk. So the next thing I want to do is sort of give a basic overview of why we think clusters should have black holes in the first place, and sort of set the stage for why the observations of these black holes in M22 are very reasonable. So let's take a look at, so again, most globular clusters today are very old populations, which means they have no massive stars today. So any black holes currently in globular clusters did not form recently, they formed a really long time ago. So to think about the formation of black holes, we really need to look at the young versions of old globular clusters. So this is sort of a cartoon image of what a cluster might look like close to the time when it formed. So again, for a typical cluster with around 1 million stars, if we assume the initial distribution of stars as a standard initial mass function, a COOP-IMF, for example, then we expect roughly 1 out of every 1,000 stars should be massive enough to collapse into a black hole. So for a cluster with around 1 million stars, we can expect around 1,000 stellar mass black holes to form. And these form very quickly within the first few to maybe tens of millions of years of the evolution of the cluster. So this time scale is just set by the main sequence lifetime of these massive stars, essentially. So early on, 1,000 black holes form. And then these black holes that form are much more massive than the stars that are found in the cluster. And as a result, because the black holes are significantly more massive, they're very quickly going to sink through mass segregation. And mass segregation is a very well understood process to operate as a consequence of dynamical friction, which is known to be efficient in any sufficiently dense stellar population. So the mass segregation timescale for these 20, 30 solar mass black holes is around 100 million years, or a few hundred million years. And the important point is that the mass segregation timescale is much less than the age of these globular clusters today, which means that for the majority of a globular cluster's lifetime, it has a configuration that looks something like this, where you have this very dense central subsystem of black holes living in the center of the cluster. Now, once these black holes mass segregate into the very high density region of the cluster in the middle, they start to interact with one another very frequently. And these dynamical interactions inevitably cause the black holes to be ejected dynamically. So over the remaining lifetime of the cluster, the remaining roughly 10 billion years, this initial population of 1,000 black holes slowly decreases through time as the black holes are ejected. And the key question that we want to ask is, if we started with 1,000, how many are left at 12 billion years? How many are left at the present day ages of Milky Way globular clusters? So as I just mentioned, the sort of first hints that most clusters still contain black holes came from these X-ray and radio observations. So there's sort of two components to these. There's these initial papers from 2007, 2008. These initially observed extragalactic black holes. So these are ultraluminous X-ray sources with luminosities in excess of the Eddington limit. And this implies the Eddington limit for a neutron star, implying that these are likely stellar mass black holes accreting at high luminosities. So these extragalactic black holes that were localized in globular clusters were sort of the first evidence. And later on, so this paper by Jay Strader in 2012, and then some subsequent papers from Jay and his collaborators found galactic versions of these. So this includes the M22 source that I already mentioned. So these are lower luminosity X-ray sources, so they're not as bright, but they also, in a lot of cases, have radio counterparts. Now for the non-globular cluster X-ray binaries in the Milky Way, many of these have dynamical mass measurements, so you can tell the difference between black holes and neutron stars from dynamical measurements. It's understood that the black hole and neutron star X-ray binaries follow very distinct planes in this radio to X-ray parameter space. And as a result of sort of the physics of the accretion flow in these systems, you can use these distinct planes of activity to tell apart black hole X-ray binaries from neutron star X-ray binaries without any measurements of the accretor mass itself. So because of the fact that most of these globular cluster sources have X-ray to radio luminosities more consistent with black holes, we argue these are potential candidates for being black holes in globular clusters. So again, this was sort of these were the first clues that clusters contain black holes. Currently, there's around 10 of these candidates total in both the Milky Way and extragalactic globular clusters. But these, to be totally honest, are uncertain because the accretion physics here there's a lot of uncertainties here. I would say the most robust evidence for black holes in clusters came more recently, in the past 5 years. So in 2018, there was a large radio velocity survey performed with the MUSE integral field spectrograph on the VLT. Essentially, they made radio velocity measurements for a large number of stars in a number of different Milky Way globular clusters over a number of epochs that allowed us to constrain the orbits of these stars and make constraints on the binary parameters. And one of the things they found, so initially they were just trying to constrain binary fractures in clusters, and sort of, I won't say by luck, but accidentally, they found this one particular star in NGC 3201, again, a fairly typical Milky Way globular cluster, that had a radial velocity orbital solution consistent with a companion star of a minimum mass of about 4.5 solar masses. So this is a roughly solar mass main sequence star with radial velocity measurements in an orbit with a roughly 4.5 solar mass minimum black hole. So from radial velocity measurements alone, you get a minimum mass from the orbital solution. Very clearly, this is not consistent. It's too massive to be a neutron star, so this is, I think, the first clear mass measurement of a black hole in a globular cluster. So this was really exciting because this was actually the first ever stellar mass black hole identified through a blind radial velocity search. And this happened relatively early on in my PhD thesis. So one of actually the earlier projects of my thesis was building an n-body simulation for this particular cluster, NGC 3201. So the goal here was to basically investigate, given the presence of this one single observed black hole in this cluster, what can we tell about the underlying population of black holes? Is this the only black hole? Does it have 10, hundreds, etc.? So essentially what we did, so this plot here is showing surface brightness versus radius for this particular cluster at its present day age, 12 billion years. So these yellow circles are the observed surface brightness profile for the cluster. So the surface brightness is essentially a measure of the density profile of the cluster. So this is generally sort of, I would say, the most useful observational diagnostic of the state of a cluster as it's observed today. And essentially what we did is we ran a large set of n-body simulations with a mass similar to NGC 3201, mass and size and metallicity similar to the observed parameters. And the one thing that we varied was the number of black holes in the cluster. So we adjusted this by essentially adjusting the number of black holes formed in the cluster at birth and retained. And when we evolved these clusters all the way to the present day, we found that based on the number of black holes left at the present day age, you produce two very distinct populations of cluster types. So on one hand, models that have large numbers of black holes left over have this very prominent flat feature in their surface brightness profile. So this is indicative of what we call the core of the cluster. So this part where the brightness profile clearly flattens out is what defines the core. And on the other hand, these models that have ejected essentially all of their black holes exhibit a very clear cusp in the inner part of their density profile. So we call these blue clusters core collapse clusters because they don't have a well-resolved core at present day. So essentially what this showed is that the only types of n-body simulations that can produce clusters with properties similar to this particular observed cluster are ones that have large underlying populations of black holes. And we actually also pointed out that this one single black hole star binary that was observed is probably one of several examples of this source in this cluster. And this MUSE group went back and did some additional follow-up observations, made radial velocity measurements for more stars, and they actually found 2 additional candidates in this cluster. So there's now 3 examples, 3 detached black hole star binaries in this cluster with mass measurements from the radial velocities of the companion stars, yeah.
This is an incredibly technical question, so I just tell you if it's not interesting. But so as you go from the little yellow dots, the observations, right, out to larger and larger radii, you're including more and more stars.
Yeah.
You know, like the typical delta number of stars from yellow dot to yellow dot. Like, because in the middle, it seems like they're all tracing like a smooth line, and then towards the outside, there's a lot more scatter. Is it just that, like, there's a lot more stars being included as you go from one dot to the next?
There are definitely many more stars being included at larger radii, and actually, yeah, so this is a technical point, but anyway, I'll mention it. There are, for whatever reason, in this observed paper, they don't include error bars, which they really should have, but these actually have larger error bars because they use fewer stars in the inner regions. So if I had included the error bars, or if this paper had included the error bars, it'd be like, yeah, the error bars are smaller out here because here you have many thousands of stars per bin, essentially. Yeah.
Can you give us some physical understanding why this black holes? Are
Yep.
they single black holes or binary black holes first?
Yeah, I'll give you, that's my next slide, is the physical understanding. Okay, so again, so this particular cluster now has 3 observed black holes in its center. From models, probably we think it has an additional roughly 100 black holes that are just not observable because they're singles in most cases. Okay, so I want to talk a little bit more about this connection between the number of black holes and the sort of architecture, the observed density profile of a cluster. So most globular clusters in the Milky Way look like NCC 3201, at least roughly. So most clusters have this very clear flat component in the regions of their density profile that is indicative of a core radius. So about 80% of clusters in the Milky Way have well-resolved cores. The other 20% look like those blue curves on the previous plot. So here's an example of M15. These are core collapse clusters, and here the brightness profile increases all the way to the center, at least as far as we can resolve it observationally. So these clusters without cores are what we call core collapse clusters. Now, it's sort of a well-known dynamical result that as a self-gravitating system of objects, all clusters naturally evolve toward a core collapse configuration. This is just because there's an inevitable flow of energy from the center to the outer parts of the cluster as a result of being a self-gravitating system. And based on the observed relaxation times of current clusters, you would actually have guessed that most clusters should have undergone core collapse by the present day. Essentially, the relaxation times are short enough that it's not obvious why most clusters don't look like this. And in fact, most of them are indeed not core collapse. So this sort of implies that in most of the Milky Way clusters, there's some internal energy source that's essentially delaying the relaxation process, delaying the collapse of the core to the present day. And our current understanding is that the presence of these black holes, especially black hole binaries, is the main dynamical source of this internal energy. So let me explain how this works. So again, initially you begin your cluster with around 1,000 black holes that sink to the center and they start interacting with each other. These black holes pair up and form binaries, both with other black holes and with other stars. And these black hole binaries that form are essentially a large source of energy as they dynamically harden through other encounters. So essentially what happens is as these black hole binaries form, they also interact with stars and they essentially transfer energy into the bulk of the stellar population where they're living. So this means that as the number of black holes slowly decreases over time, as the black holes are ejected, the internal heating, the dynamical energy from this black hole subsystem slowly decreases, the core radius shrinks until eventually after essentially all the black holes have been ejected, you're able to attain what would be a core collapse architecture for your cluster. So we think the clusters that still have a large cores still have a large fraction of their initial black holes, while the clusters that are core collapse have gotten rid of essentially all of their black holes by the present day. So the next question that we can ask, and again, given the fact that most clusters today are not core collapse, this implies that most clusters still probably have a large population of black holes. So the next question that we want to ask is, what is the main physical feature that determines why some clusters still have a lot of black holes while other clusters don't? And this can be explained, I think, fairly intuitively by just variations in the initial density of a cluster at birth. So by looking at young massive clusters in the local universe, so we sort of think these are the young analogs of protoglobular clusters. Obviously, old globular clusters have been young at very high redshift, so they're hard to observe. But young higher metallicity clusters we can observe very well. So these young massive clusters in the local universe have a very clear range in initial sizes, about an order of magnitude spread in initial sizes. And this then turns into a spread in initial densities. So using this same initial spread in densities and running n-body simulations that evolve these clusters forward to the present day, we see this produces a very large range in the numbers of black holes retained and also in the surface brightness profile of the clusters at present. So essentially what happens, these are 3 simulations with all the same initial number of stars. The only thing we're varying is this initial size, which sets the initial density. All 3 of these clusters form around 1,000 black holes initially. So this is again just set by the stellar evolution of the massive stars. And then the clusters that are born the most dense essentially evolve the quickest because they're denser, they undergo more dynamical encounters. These clusters are able to eject their black holes more quickly. Essentially, their dynamical clock is running more quickly because of the fact that they're more dense. So this blue curve model is able to eject essentially all of its black holes by the present day. And again, showing its brightness profile at present, this is able to produce a polar collapse cluster. On the other hand, models like this orange model here are born relatively diffuse, lower density. Their black holes have longer times between encounters. The clusters evolve more slowly. They still have a large population of black holes at a Hubble time. Now, if you evolve this model forward in time, let it run longer, eventually it would get rid of all of its black holes. But because this cluster is evolving slower dynamically, it still has a large population of black holes. As a result, at the present day, this cluster still has a large core. It's similar to clusters like, for example, NCC 3201 at present. Yeah.
Just curious, is there like a self-similar solution on the left? Like you could imagine just scaling time by the initial radius or something like that, and it's a single functional form. That they all kind of look the same, but I just wondered if that.
Yeah, and people have kind of done this. Qualitatively, definitely you can do this. You lose some of the details when you do that, but yeah, I'd say more or less there is.
Quick question about how this all depends on cluster mass.
Yeah, good question.
I mean, I guess this is a bit ambiguous because we don't know in many cases exactly what the initial mass was, but how does the distribution of relaxation times, if you just consider the width of the distribution, vary with the mass?
It varies with the mass, but it's not as steep of a power as the variation with radius. So,
well, I guess what I meant is observationally, you go to higher mass clusters.
Yeah.
Do they tend to have faster or slower relaxation?
Slower. So higher mass clusters have generally longer relaxation times. So it's harder to eject all of the black holes, for instance, in a more massive cluster than it is in a lower mass cluster. Okay, so hopefully I've kind of convinced you that there is a lot of evidence pointing toward the fact that most clusters probably contain a lot of black holes in their centers today. Dozens to even hundreds of black holes. Now, most of these black holes, which we know this from n-body simulations, are isolated. They're single. They don't have companions. We expect maybe a binary fraction of a few to maybe 10% in most clusters. So perhaps a handful of black hole star binaries that could potentially be detected in each cluster. So again, for the Milky Way population, where we have roughly 200 globular clusters, this then implies there should be several hundred of these that could potentially be detected. But again, we only have 10 that we've observed so far. Now, a big part of this is just because of observational bias. Only a handful of clusters have been surveyed with enough precision to be able to find them in the first place. So the sort of natural question is, can we observe this much larger underlying population? So this large program that I've started, I'm going to be sort of continuing at UCSD, is the first ever blind radial velocity search for black holes in a large number of Milky Way globular clusters. So essentially, we're building off of what the MUSE program did for NGC 3201 and a few other clusters in the Milky Way. And essentially, we're making radial velocity measurements of large numbers of stars in the centers of globular clusters that we think from N-body simulations have large black hole populations, and trying to measure their orbits and then ultimately find the stars that might potentially have black hole companions. So the biggest thing that's a challenge about this is you need at least 15, even 20 radial velocity epochs to measure the orbit from these systems. So, and most of these systems have year, 10-year orbital periods. So it's kind of the biggest observational challenge is building up enough epochs that you can make precise radial velocity orbital solutions. But we're getting there. We got 7 nights on both KCWI on Keck, which is sort of Keck's interval field spectrograph, also Magellan's interval field spectrograph this year. So I think in the next few years, few to 10 years, it's very likely we'll be able to detect additional black holes in globular clusters through this radial velocity method.
Sorry, I'm a little confused about the single statement. So first you said you need black hole boundary to hold up the cluster. Sorry, this is a slide.
Okay.
To hold up the clusters. So I was expecting then you're going to say every black hole should be boundary, but then you make a statement saying you expect most of them to be single.
That's right. So most are single, but the key is that even a single the energy reservoir of a single black hole binary is actually, we could go through this maybe after on the blackboard. So the energy reservoir of a single black hole binary is actually comparable to the total energy of the core of the cluster. So even if most black holes are single, even just a handful of black hole binaries throughout the evolution of a cluster at a time is sufficient to provide a large source of energy into the cluster. So the black holes are the much larger underlying population of black holes is necessary to form the binaries, but the binaries is the main source of energy. And the important thing is that the binaries are not static over time. The binaries are very dynamically evolving. So there's maybe a handful of binaries present at any given time in the cluster, but these are changing significantly as the cluster evolves because of the fact that the binaries are being driven to merger as a result of interactions with the other single black holes. So
But the single one is a prediction from stellar evolution. So just that if you run your ES primary service and you end up with black hole, most black holes are the same.
Yes, that's correct. That's also a little bit motivated by observed binary fractions in globular clusters, which are very low, less than 10%. So we know most stars in clusters are singles.
Is that just because of dynamical interactions, or?
It's not entirely obvious why. Probably it's dynamical interactions that's contributing, although it's could be the case that at lower metallicities, the binary fraction is lower, or that stars in clusters form in a different way than stars in the field. It's a longer discussion, but it is quite clear that the binary fraction in old globular clusters is lower than the binary fraction in the galactic field, for instance. Other questions about this stuff? So this is like sort of the main basics. So this is good. This is a good part for questions, and then the next thing I'm going to do is sort of applications. So, other questions? Okay. So these black hole binaries and clusters are also closely related to the sort of other method for observing black holes over the past few years using Gaia. So Gaia is this really great observatory for making astrometric measurements of stars. And one of the exciting results from Gaia is the detection of 3 detached black hole star binaries that have astrometric orbital solutions. So astrometric solutions are really nice because they not only give you a minimum mass, they give you an exact mass because you can measure the inclination for the binaries. So these 3 Gaia black holes have very well constrained black hole masses. So the first 2, these are roughly solar mass stars, roughly solar metallicity, in orbit with roughly 10 solar mass black holes. And then this third one in particular is really interesting because this is a 30 solar mass black hole with, again, a roughly solar mass star, but very low metallicity, less than 10% solar metallicity. So this actually is the most robust piece of evidence yet we currently have that black holes at low metallicity form with higher masses. This is a very robust piece of observational evidence for this statement. The other interesting thing about this source is it is in the halo of the Milky Way, and it's both chemically and kinematically associated with a stellar stream. And the stellar stream has a mass and velocity dispersion that almost certainly points to the fact that it was formed from a disrupted globular cluster. So I think this particular source formed dynamically in a globular cluster that was then later disrupted through the tidal force of the Milky Way. So this is sort of the analog of the NGC 3201 sources that happens to be in the halo because the cluster it was born in basically did not survive in the present day. So this is sort of an additional piece of evidence that black hole binaries are forming dynamically in globular clusters. So again, astrometric solutions are really nice because they give you an exact mass. Radial velocity solutions only give you a minimum mass. So you can actually also do astrometry for the globular cluster black holes. So you can't do this with Gaia because these sources are too far away. But HST is actually a really good astrometric observatory. So there's been a lot of astrometric measurements of stars and clusters that have been used to make proper motion constraints. I was involved in a proposal that actually got 10 orbits of HST time this year to make astrometric measurements of 2 of the black hole binaries in NGC 3201. So these have only radial velocity solutions now. This plot here is basically doing a mock observation, taking 10 evocs of astrometric measurements of this source, and then showing the inclination that you would potentially measure. And what we can see here is that depending on the inclination that we measure for this source, you can distinguish black hole masses similar to, for example, this low mass microlensing black hole, roughly a few solar masses, from 10 solar mass black holes like the Gaia, first 2 Gaia black holes, and also some of the more massive LIGO-like sources. So these astrometric measurements will be really valuable for actually pinning down the exact mass of black holes and globular clusters and giving us some more insight into the details of these populations. So as we hopefully discover more black holes through radial velocity measurements, ultimately we'll be able to follow these up astrometrically with either HST or JWST going forward to constrain the mass more directly. Okay, so with sort of this basic sort of framework in mind, the last thing I want to do, I'm going to go through each of these pretty quickly, is discuss sort of 3 applications of this that I think are very relevant in sort of the current age of astronomy. So binary black hole mergers and implications for LIGO, gravitational-wave sources, collisions of black holes and stars and the ability to produce high-energy electromagnetic transients, and then at the very end I'll talk a little bit about other stellar remnants, white dwarfs and neutron stars, and why those are particularly exciting in core collapse globular clusters. Okay, so I'm going to show just one slide on sort of our simulation details, but we can talk later if people are interested in the details specifically. So this is an n-body type simulation code that uses this well-understood Monte Carlo algorithm that's been around for a few decades now to basically solve the n-body problem for globular clusters. So a few sort of really key features. So one is that we model the evolution of individual stars using the cosmic population synthesis code. So this is really important because it allows us to self-consistently predict the numbers of black holes, neutron stars, white dwarfs in the cluster over time. But it also allows us to make mock observations of the clusters because we know the masses and luminosities of the stars in the cluster. So this allows us to do things like make observations of surface brightness profiles, velocity dispersion profiles, things that you would use to actually compare models to observations. So this allows us to really fine-tune our models based on making matches to observe clusters today, as opposed to, for example, treating the numbers of black holes and things like this as free parameters, which would be a little bit more suspect in terms of predictions we're making. So just as an example, a lot of the results I'm showing in the next handful of slides are from this large catalog of CMC simulations we've produced over the past 5 years. So this is sort of the first large catalog of simulations to reproduce the full distribution of Milky Way globular clusters. So this is a very good representation of sort of local universe globular clusters as they're observed at present day and also throughout their history. So again, I can chat with people more individually about the details of the simulations if you're interested. Okay, so gravitational wave sources. So LIGO Virgo has now detected over 100 binary black hole mergers through gravitational waves. Obviously, these have been tremendously valuable in many different aspects of astronomy and physics, but I think despite all of the major successes, this sort of very basic question of how these sources form in the first place still very much remains uncertain. So canonically, there's sort of two main formation channels people have investigated. There's formation via isolated binary evolution, where a pair of massive stars are born together in a binary, they evolve together, they form a pair of black holes that ultimately converge in the Hubble time. This channel is very well motivated because, for instance, there are many high-mass X-ray binaries with black holes observed in the Milky Way and other nearby galaxies. So we know at some level black holes can form in isolated binaries like this. And then the other channel, major channel, there are many others as well I'm not going to go into, is sort of dynamical formation. So here, instead of a pair of black holes forming together through a pair of initially bound massive stars, two black holes can form separately through two initially unbound stars and then later be paired up through dynamical encounters. So for this dynamical channel to operate, you have to be living in a really dense stellar population so that the rate of encounters between stars is high enough to lead to a non-negligible formation rate for these black hole binaries. So globular clusters is one example of a really good population for forming these binaries dynamically because they're very well-known dense populations of stars. There are other things too, AGN disks, massive galactic nuclear star clusters, but globulars are what I'm sort of focusing on here. And one of the sort of things that's gotten a lot of people excited about the globular cluster channel specifically is if you take these n-body simulations that again can match very well observed features of Milky Way globular clusters today, and if we distribute these simulations in the local universe in a way representative of our understanding of globular clusters, then the volumetric merger rate of black hole binaries in these systems is consistent to within a factor of about 10 of the rate that's been inferred from LIGO so far. So blue here is showing the volumetric merger rate out to the redshift around 1.5 from LIGO, from their current catalog of published detections. And these black curves are showing the black hole merger rate from clusters with a few different initial virial radii. So again, the virial radius is sort of one of the key diagnostics early on that defines the state of the cluster initially when it's born and ultimately determines the evolution of the black holes over time. So the main point is just that for this range of observed initial sizes, which again is motivated by observed properties of young massive clusters, the black hole merger rate in the local universe is consistent to within about an order of magnitude of the rate that's inferred from LIGO. So this is at least hinting that clusters can potentially contribute to the LIGO population.
Hi, sorry to interrupt. A quick follow-up though of my previous question. This is why I was asking about how, if you consider the range of RV as a function of the cluster mass, how that scales. Is there an expectation that more massive or less massive clusters are contributing more to the total rate?
Yeah, so let's see if I can answer this question succinctly. On the other hand, on one hand, there are many more low mass clusters just because it's pretty well understood observationally that the mass function of clusters is roughly m to the minus 2. So there are many more stars born in lower mass clusters. So that would potentially help boost the low mass merger rate. But the problem is lower mass clusters generally produce black hole binaries that don't have merger time sufficiently small to merge within the Hubble time. So the rate from lower mass clusters is not as high as you might guess just from the pure number of stars in clusters. Now, very massive clusters are much more efficient at merging black holes, but in some ways they're actually too efficient because the black hole binaries form in very massive clusters. So these are 10 to the 7, 10 to the 8 or more nuclear star clusters. There, the black hole binaries that form are actually very compact, and they generally merge very quickly, so potentially at high redshift. So as it turns out, globular cluster type systems, 10 to the 5 to 10 to the 7 solar masses in size, are sort of right in the sweet spot for producing things that merge within a Hubble time or within maybe a few billion years, which is what you want for producing LIGO sources that merge in the local universe. So yeah, there's lots of factors that contribute beyond just the role of mass in terms of the number of black hole binaries produced. There's also the effect on the merger times from the different cluster masses. And then, okay. Okay, yeah, thanks for the questions. Okay, so aside from the rate argument, there's also some other hints that might point us toward the role of clusters or dynamics in forming LIGO sources. So I think one of the more interesting things that's been observed from LIGO is a large number of very massive black holes in excess of 40 or 50 solar masses. So from a stellar evolution process known as the parent stability, essentially this is a process that drives from electron-positron annihilation in the very hot cores of very massive stars. This process is expected to lead to a significant amount of mass loss for massive stars, for sufficiently massive stars, right before they collapse. And the expectation from stellar evolution theory is that the parent stability process would lead to essentially a dearth of black holes, or potentially even an absence of black holes, above roughly 40, 50 solar masses up to maybe 100 solar masses. So if the star is very massive, then essentially the center of the star would be hot enough to overwhelm the parent stability altogether, and you could potentially get direct collapse. But in the range of roughly 40 to 100, 120, you potentially could have this gap in the black hole mass function from the parent stability process. So what's been really interesting from LIGO is they've observed this tail in the black hole mass function clearly extending into where we would expect this black hole mass gap to be, which begs the question, is there something we're missing about the evolution of these stars, or is there some other mechanism operating? So globular clusters, or any dynamical environment, actually give you a really natural way to populate this mass gap through a couple different scenarios. So one scenario involves repeated black hole mergers. So if you form two initially lower mass black holes subject to the parent stability, say 40 solar masses here, if these black holes merge, because they're still living in a dense environment, they can eventually pair up with other black holes and merge again, a second, sometimes even a third or fourth time. So this gives you a way to build up more massive black holes than you would have formed through single star evolution alone, can give you a way to populate this mass gap. You can also form massive black holes through mergers of stars. So before the stars collapse into black holes, they can merge with one another, create sort of exotic stellar objects that would not normally be able to be formed through normal stellar evolution, that again could potentially give you a way to form mass gap black holes that would otherwise not be possible. So this black curve then is showing from the sort of same set of MBI simulations I showed before, the distribution of primary masses for all the black hole mergers we expect at redshift less than 1. And you can see that this gives us a way to populate this mass gap in a way that's roughly consistent with the mass distribution that's been observed from LIGO so far. And then certainly there's other hints as well. There's other clues from the LIGO data that can be used to constrain the role of dynamics. So one of the key features of black holes assembled dynamically is that they should be have roughly isotropic spin orientations. This is because the black holes are assembled separate from one another, so when they form a binary, there's essentially no memory of the initial spin distributions of the black holes. This potentially is very different from isolated binaries, which involve various gas phases, common envelopes, tidal interactions, et cetera, that potentially align black holes. So any preference in the LIGO data for isotropic spin distributions would potentially point toward dynamical origin. And then eccentricity is another big one. So eccentricity is kind of a challenge at present to pull out of the LIGO data, but in principle, if eccentricities can be measured for some population of the black hole binary mergers, this could also be used as a clue to point toward dynamical origin, because sources assembled dynamically are expected to have much larger eccentricities than the ones that are formed through isolated binary evolution. And looking forward, the sort of next generation millihertz detector, LISA, is actually going to be really valuable for making eccentricity measurements, essentially because LISA will observe LIGO-like sources at lower frequencies close to the time that they formed. So LISA will be able to very effectively measure eccentricity distributions. These curves here are showing eccentricity distributions at sort of the peak sensitivity for LISA in in frequency. For a few different cluster populations of red and blue compared to the galactic field, you can see these very clearly produce distinct eccentricity distributions, so potentially based on distributions that LISA observes, we can use to point toward the role of dynamics. And then the last thing I'll say about gravitational waves, certainly it's very clear we've only just scratched the surface of observationally what's possible, both in the coming years, very short term, as LIGO continues to make more detections. The population of both black hole mergers and neutron star mergers is expected to increase significantly. Moving forward into the proposed next generation detectors, it'll increase even further. So I think there's a lot of reason to be excited over the next years and decades about the prospects for detecting additional compact object binaries of gravitational waves and ultimately using these to constrain the underlying populations in globular clusters, for instance. All right, let's see, how am I doing on time? Okay, I'm doing good. These two next two are a little bit shorter. Okay, so the next thing is sort of switching gears a bit. This is looking at, instead of mergers of pairs of black holes, mergers of black holes with stars in a globular cluster. So again, we know that black holes and stars are dynamically interacting in globular clusters because there are now several examples of observed black hole star binaries in these systems. So essentially, closer dynamical passages between black hole stars rather than forming binaries could potentially cause direct collisions between black holes and stars or tidal disruptions. And these potentially would give rise to very bright electromagnetic transients. So predicting the rate of these black hole star collisions is fairly straightforward from the perspective of n-body simulations. Essentially, you have a cross-section for collisions, which is set by the radius of the star. And essentially, during the course of an n-body simulation, you can basically just count up how many times a black hole crosses within a collision cross-section for a star. So from these types of simulations I was showing, we predict a rate of roughly 1 collision per 100 million years. Collectively, in the sort of local universe population of globular clusters, this translates to a rate of roughly 1% of the core collapse supernova rate. So definitely lower than the core collapse supernova rate, but still definitely a high enough rate to potentially produce a large number of detectable transients. So just to sort of give you a rough idea, the most typical black hole star collision that we expect will involve, again, a stellar mass black hole, 10 to 30 solar masses in size, and then a low mass star, solar mass or lower. The reason the stars are generally lower mass is because globular clusters spend most of their time as very old populations with low mass stars. So basically, there are many more low mass stars than massive stars, so you're more likely to collide with lower mass stars from just a rates perspective. Okay, so given this rate, let's sort of investigate what happens during these transients. So this here is a hydrodynamic simulation of a solar mass main sequence star. This is this red thing, combining with a 10 solar mass black hole. And this is basically a grazing collision, so the black hole is essentially hitting the star edge on. So there are a few key differences here compared to sort of a canonical supermassive black hole tidal disruption event. So one key difference is that generally these lead to tidal capture, meaning they lead to multiple passages. So this is essentially because the relative velocity at infinity of these two objects in the cluster is very low compared to essentially the escape velocity of the black hole. So that means these collisions are essentially parabolic initially. So generally the star comes in, is disrupted a little bit on the first passage, becomes bound, and then undergoes multiple passages before being disrupted fully. So the other key point, which is related to this first one, is that the vast majority of the mass, at least 50%, ends up bound to the black hole. And this mass essentially settles into a roughly disk-like configuration. So we know it's going to settle into a disk because you have angular momentum involved in these collisions. And essentially that angular momentum, when it translates into the ultimate configuration, settles into a disk around the black hole. So qualitatively, I think really the clear analog of these sources is a massive rotating star, like a collapsar. So essentially, these are sort of a way to assemble collapsar or massive star-powered transients using an old stellar population. You're essentially taking a black hole and embedding within a thick rotating envelope that eventually produces a transient that's powered by ultimate accretion of the disk onto a black hole. So the prediction that we make from doing light curve simulations of these events is that a small amount of the disk mass ends up accreting onto the black hole, producing an X-ray transient, but a large amount of the disk mass ends up being lost from the disk and blown out as a wind from the disk because of the fact that the inflow in these systems is very highly super Eddington. So the amount of mass actually accreted is pretty small. So what this means is essentially you're left with a disk which accretes onto the black hole embedded within a very thick envelope of material that reprocesses the energy from the inner disk and then produces a reprocessed powered transient that ends up peaking in the optical or UV after the reprocessing from the disk wind. So the transients we expect to be produced from these are of order 10 to the 42 up to maybe 10 to the 45 ergs per second, depending on the accretion efficiency exactly. And in the past, this is the past year, there's actually been a number of potential candidates for these transients that have been detected. So these three events were all found with a few different optical all-sky surveys, ZTF, Atlas, etc. These three transients are all found in massive elliptical galaxies that are quiescent. No star formation going on, or very little star formation. So the lack of star formation in these galaxies already makes it very difficult to explain these using massive star-powered transients like core collapse supernovae, because there aren't really massive star populations in these quiescent galaxies. The other really interesting feature is all three of these transients are observed with very high offsets from their hosts, 10 kiloparsec or so offsets from the host centers. So that makes transients powered by a supermassive black hole not really very viable because these clearly are offset from their host galaxy centers. So all three of these host galaxies are consistent with populations of thousands of globular clusters, typical of other massive elliptical galaxies. And the light curves observed for these simulations are also consistent roughly with the predictions we would expect from these transient models that we've been producing. Now, these are still candidates. You certainly can't say robustly that these are these black hole star collisions. But this can be tested, and the way this can be tested is with JWST by looking at the location of these transients at redshifts of roughly 0.2, maybe a little less than 0.2 on the far left. JWST can actually resolve a host cluster at the location of these transients. And certainly the detection of a host cluster at the location of these transients would, I think, provide the clearest piece of evidence that these are indeed being dynamically powered by dynamical processes and clusters. So we're in the process of trying to create a JWST program to follow up these transients, potentially test this a little bit. Okay, and then the very last thing, last couple minutes here, I want to say at least a couple words about white dwarfs and neutron stars. So again, based on sort of the first part of the talk, we think most globular clusters, which are not core collapse, have very large cores, probably still have a lot of black holes in their centers, tens, hundreds of black holes in their centers. But the subset of clusters that is core collapse, we think has ejected nearly all of their black holes, and in this case, the most massive stellar remnants in these clusters are going to be the neutron stars and the more massive white dwarfs. So in this case, in these core collapse clusters, the white dwarfs and neutron stars are going to sink to the center via mass segregation, analogous to the way the black holes formed a subsystem at earlier times. And this makes these core collapse clusters really great places to look for interesting white dwarf and neutron star dynamics. For example, mergers of white dwarfs and neutron stars. So I would say the most straightforward way to observe a neutron star is as a radio pulsar. So once a neutron star forms, for example, via a core collapse supernova, it is born with a very high magnetic field. It's born generally rapidly rotating. They're very bright radio sources. So a nice way to sort of characterize the evolution of a neutron star is with a PP dot diagram, spin period derivative and spin period of the neutron star over time. So this green star is sort of quintessential neutron star like the crab pulsar, where it forms after it is born. Now, once a neutron star forms, it's potentially observable as a radio pulsar. It slowly evolves over time as it spins down via magnetic dipole radiation. And as the neutron star spins down, it eventually becomes lower in luminosity until eventually it falls below this so-called death line, which is an empirical boundary below which no radio pulsars are observed. So these little blue points in the background are all of the radio pulsars that are observed in the Milky Way. So for an object like the Crab pulsar, for instance, which is born with a magnetic field of around 10 to the 12 Gauss, the observable lifetime before it evolves below the death line is around 10 to the 8 years. Now again, most globular clusters are 10 to the 10 years or older, which means that any neutron star that formed early on should not be detectable at present day, because it will long ago have spun down, it will no longer be observable as a radio source. But you can potentially reactivate a neutron star as a radio source by spinning it back up if it accretes material from a binary companion. So these are the sort of classic millisecond pulsars. There are many of these millisecond pulsars observed throughout the Milky Way, and in globular clusters in particular, there's several hundred millisecond pulsars known. So it's very well understood that globular clusters are really efficient ways to dynamically form neutron star binaries that lead to spin up of neutron stars and millisecond pulsars. Now, a really interesting subpopulation is this population of 6 pulsars and clusters that are very clearly not radio millisecond pulsars. So this subpopulation of 6 have slow spin periods of order a second, indicating that they have apparent ages that are very young. So these have inferred ages of roughly 10 to the 8 years or less, consistent with what you would have expected for something like the Crab pulsar that was born and spun down over time. Now again, these are really weird because, again, in old populations like globular clusters, we would not expect these pulsars to form because clusters have no massive stars. And all 6 of these objects are found in core collapse globular clusters that, again, we think have ejected all their black holes and eventually have very dense subsystems of white dwarfs and neutron stars. So the sort of hypothesis that I've been working on developing is that this subpopulation of 6 young pulsars in old clusters formed at late times via mergers of massive white dwarfs. So essentially you have a pair of massive white dwarfs that merge and ultimately collapse into a neutron star. It would potentially be observable as a young pulsar today. And closely related to this was detection of a repeating fast radio burst in another old globular cluster in M81, nearby galaxy, about 3.5 megaparsecs away. So the origin of FRBs is very much uncertain. I'm not going to go into this at all. Most people think that magnetars formed recently in core collapse supernova is a really good way to form fast radio bursts. It's motivated in part by an FRB in the Milky Way that is known to be associated with a known magnetar. So this particular source is really interesting because, again, we don't expect young magnetars to be found in old globular clusters. This potentially is also evidence of the formation of young neutron stars in clusters at late times via channels like white dwarf mergers operating. So potentially there are multiple clues pointing toward the merger of white dwarfs in these core collapse clusters that would produce young neutron stars. And there's sort of all sorts of reasons to be excited about radio astronomy in the context of globular clusters over the next few years. New telescopes that are very massive, really sensitive, like FAST in China, Meerkat Array in South Africa, are going to increase the number of millisecond pulsars both in clusters and elsewhere in the Milky Way by a significant fraction. Just to give you 2 examples, in the past 6 months, there's been 2 additional of these young slow pulsars found with FAST in the Milky Way. And there's also this really cool source found with Meerkat that's a millisecond pulsar in a binary with a black hole, a low mass black hole, which is a very exciting source for a number of reasons, also in a core collapse cluster. Okay, so that's pretty much everything I have. I think, again, there's a lot of reasons to be excited about globular clusters as laboratories for studying compact objects and compact object dynamics from the perspective of gravitational waves, radio astronomy, various transient astronomy, things like the Vera Rubin in the next few years, and a lot of reasons to be excited about the prospects for detecting more of these compact objects and clusters through a variety of mechanisms. So thanks again. Happy to answer questions if people have more questions.
Yeah, I had a question just about the last topic, those young pulsars found in the clusters. From the radio timing, do we know anything about possible binary companions? Can we tell if they're binaries at all? Is there any evidence that these would be sort of progenitors of neutron star mergers we might see later in gravitational waves from these systems?
So for these, so many of the millisecond pulsars are in binaries. And that's more obvious because presumably the fact that they're in a binary is why they were spun up. For these 6, I don't remember which, 5 of the 6 are singles, and that's known pretty clearly. One of them is in a binary. Maybe we could talk more about the details of that. The 6 that are single are all found in the center of their host cluster, which is sort of consistent with if they did form from white dwarf merger, that should have happened in the center of the cluster because that's where the white dwarfs are most living in a most dense population. Certainly a single makes more sense because if 2 white dwarfs merge, it should produce a single neutron star. The one that's in a binary is anomalous because it's actually observed at a very high offset from the host cluster center, well outside the half-light radius actually. So probably that one formed a binary later on through another dynamical encounter and then was actually ejected out into the outer part of this cluster through the exchange encounter. But yeah, we know we can use the binary or lack of binaries to tell us other things as well.
I love what you've been talking requires comparing your models to observations. No model is perfect. What do you think are the new areas where they could be improved?
Well, I think that the observations of old globular clusters are very robust, I think. Observations of young globular clusters are not robust at all.
And CMC does not work for young ones.
That's right. So the best thing that we can improve, so I think that comparing our models at late times to old cluster properties, we can do well. But understanding the exact initial conditions of clusters and using observations to inform those initial conditions, there's a lot of room for improvement on both the simulation and observational side. So by far, that's the biggest area for improvement. It's not entirely obvious whether, I mean, you can imagine for the set of initial conditions that we have started with now, which I think are fairly well motivated as far as we can tell, we do a very good job of mapping from initial conditions to the present day properties. But it's not obvious that you couldn't have chosen some other set of initial conditions that also evolves the present day properties. And that, yeah, again, there's a lot of room for further work there.
A question about the off-center TDE candidates.
Yeah.
Wouldn't they be easier to make with intermediate mass black holes? I mean, wouldn't you be selecting out preferentially star clusters that had intermediate mass black holes?
Yeah, I think that absolutely would work as well. And potentially that would also give you an easy way to make the transients even brighter, just because a IMDH would be able to produce a brighter transient than a stellar mass.
Exactly, because they were like peaking at 10 to the 6 or more Eddington, weren't they?
Yeah, exactly. I think that if these are observable, they have to be super Eddington, which I think is reasonable to some extent because of the fact that the inflow rates are almost certainly the inflow material is going to be vastly in excess of the Eddington limit. So as long as there's some way, if you form a jet or there's some way for the energy to escape unabsorbed, which I think is plausible given the fact that these are essentially disk-like geometries. But anyway, I understand the question about the IMDHs. So I would say that there's with a couple of exceptions, there's not clear, robust evidence that most or even any globular clusters contain intermediate mass black holes. So I think
I understood about that, but even if the fraction is small, the cross section is much larger, right? So isn't that the case? So you don't have to have a large fraction to dominate the rate of TDEs.
True. I think that's true. If we are comfortable making the assumption that some fraction have IMDHs, I think it requires much less of I think the stellar mass black holes are more easily motivated just from a stellar evolution argument than IMDHs. Yeah. So I think it's a very good question. I've generally steered clear of the IV question just because there's less observational evidence for those. But it's a very fair point.
Thanks. Yeah.
Any more questions?
The idea that in a cluster that black holes could grow in size just by repeated mergers. I thought that in the globular cluster, if two black holes merge, they would tend to get kicked out by the gravitational wave kick that they get.
Yeah, exactly. That's right. So that is the main mechanism that prevents runaway growth of black hole supermergers. So you could eventually have, so you really only need to have one merger to get a sort of mass gap event. So for example, if this merger can be retained, most of them probably are not because many of them probably do get ejected. But if one of these can be retained, then it can merge again, and then almost certainly the chances of it being retained twice is very small. Now the kick of this initial one is highly dependent on the spins of the black holes initially. Probably most black holes, this is uncertain, but from stellar evolution arguments, probably most black holes are born with small spins. So getting this first merger to be retained is, I think, more straightforward just because because of the fact that these initially have small spins, this one is not going to get a big kick. But then this object is going to absolutely have high spin because of the fact that it's coming from a black hole merger. So now when you have a highly spinning black hole merge again with something else, the chances of it being retained the second time are very small. So you could potentially get 80 solar mass black hole mergers, but getting very massive, like extended series of black hole mergers is difficult for the exact reasons you mentioned. Now the exception is if you go to very massive clusters where the escape velocity is very high, then you could potentially always retain things because even though the gravitational waves are providing kicks, the escape velocity is higher. But for a typical globular cluster, you're probably going to get maybe one or at most two repeated merger events.
Any other questions? Any questions online? If not, let's thank Kyle again.
All right.
So for the eccentricity plot you showed, the ones merging cluster is much higher than ejected is because there's gravitational wave captures, and also for the ejected ones, you also in spiral and the triangularize it a little bit.
So the reason that the main reason was the source line so it kind of is
I'm curious